And Jamie is here today, David.
Yes, I am here.
So it's going to take me a minute to get out all.
That's fine.
Sorry.
Well, I had intended to go today. And Rob said that he was going to be out. He said, can I wait till
We got everything switched, Andrew.
Yeah, well, she's here, so I'm not sending her to Kingsport to justify that swap. And apparently there is a symposium in that room somewhere. It's on the wall by the thing.
I think Shannon has it, really.
He says he left it up there for you guys.
Wonderful.
Well, you got a week to find it.
Yeah, there you go. Maybe I misunderstood him, but that's...
No, it makes total sense that you would be here because Rob is out. And I'm watching his class, which is yours,
Well,
and my class.
Two classes. That's what he told me.
And
He said, so if you don't mind, could you wait till the next week? Because if you having two classes, I forgot about that part.
but they didn't really tell me about it. I just kind of overheard that it might be a thing at some point. And then yesterday I got an email a message from Gary saying that you had emailed saying you were going there. And so he got an email, I should say. It didn't say that you did it, but so
Right, I'm sorry.
it's not at all your fault. Don't sweat it.
It's our motto, Jamie. Just adapt and handle it.
Sipper Gumby, always flexible.
Well, sorry for the confusion this morning, everyone. So, yes, I do eventually try to go to Kingsport at some point during the semester. Hasn't happened yet, so I like to go over there at least once during the semester, though, and that way you all too can see what it's like from their point of view. You know, that's kind of different, right? So, anyway, what we're going to do today, I just went ahead and passed back the papers over here, the homework papers, and we don't have anybody in Kingsport yet, is that right? Have we? Yeah, nobody's there at this point. Okay, they come in. They'll come in late, so that's what'll happen. I think maybe we'll see. But okay, so
There was a big wreck right down on Stone leading into here, so a lot of people are late today.
Oh no. Okay, well that makes sense. We have a lot of that. It seems like anymore coming in the morning. So. But we're going to look over this homework paper that I gave back. We're going to do that first, and then we're going to continue on in this chapter 7. And then the other thing we're going to do today is finish up that sum and difference section, which is part of chapter 7. Okay? So we're going to do that as well. And next week, we're having a test. Do y'all remember when that test was? Yeah, the 30th. So next Thursday, we'll have a test. Okay? Now let's see, my computer, where'd it go? There it is. We've almost got it rolling here. So. So first, if you'll just keep out that homework paper I just gave back to you. Now, did everybody over here get their homework paper back? You just came in, right, Rachel? If you did, if you did really well on the homework and understood it all, just bear with me just a moment. I usually don't go over something like this in the class, but because we are having that test next week, I want to go back through some of this because I felt like there was a little bit of confusion and some things that maybe y'all need to start going back and reviewing on just a little bit, okay? So let me switch over here to the computer a moment. And that first one, the cosine of the inverse sine of -2/9, let's look at that one first. Oh, I'm sorry, it's the cotangent of the inverse sine of -2/9. We know that there is not an angle that has a sine of -2/9 that we know about on the unit circle, right? We don't know about that one. So we're going to draw this thing in, and this is where we have to remember about the inverse sine, where it's defined. The inverse sine was defined from -pi/2 to +pi/2. So in these two quadrants, when we were looking at that, and because we're looking at an angle that has a negative sine value, we have to put it down here in this quadrant. Okay, so we're going to put theta down here, and that would have a negative sine value if it's down in the fourth quadrant. We know then that the sine of theta, we're drawing an angle, theta, so that the sine of theta will be -2/9. That's what we're doing. We're manipulating here, okay? We're going to make this thing happen. So we want the sine of theta to be -2/9. We know that sine is y over r. So that means what we have here is y is -2 and r is 9. We don't know x, but we can find x now, okay? And the reason we want x is because we really want the cotangent of the angle that has a sine of -2/9. That's what the question, is really asking for. Okay, so we want the cotangent, and the cotangent we know, cotangent of an angle is x over y, right? Okay, so we need to know what x is. So x squared plus y squared equals r squared. X squared plus 4 is 81. X squared is 77. X must be the square root of 77. We do need to ask ourselves, is it going to be positive or negative there? It's going to be positive because we're out in the first quadrant there. So x is going to be the square root of 77, meaning the answer to the question is going to be the cotangent of the angle that has a sine of -2/9 will be our x value over our y value. Okay, so that's why we get negative square root of 77 over 2. All right, any questions on that one? Looking at it today, any questions there? All right, let's move on then. I don't want to spend too much time on this, but just go through it here real quick with you. This was calculator problem, inverse tangent of -2.1. So your calculator should be in radians. We talked about when we did inverse functions, we wanted our calculator in radians. So go on the calculator, and we would, on most of them, you're going to put it in second function tangent, and then your negative key, which on the graphing calculator usually looks like this. Do not put it in parentheses. That's just what the key looks like, okay? Second tangent, which means the inverse tangent of -2.1, enter. And that should give you the radian measure, which appeared to come out to be approximately -1.13. Okay. Third one was a little different because it was the inverse cotangent of a negative value. Whenever we have an inverse cotangent of a negative value, if we use the inverse tangent to get the answer, then what we have to do is think about, which quadrant will we end up in, because the inverse tangent is defined from -pi/2 to +pi/2, whereas the inverse cotangent is just defined from 0 to pi. So we've got a little bit of a difference going on there. They're both in the first quadrant, but the inverse cotangent's in the second quadrant also, while the inverse tangent is in the fourth quadrant. So when we use the inverse tangent, for this negative value, we're going to get an angle that's down in the fourth quadrant. But yet the question really said inverse cotangent, so we need the corresponding angle up in the second quadrant. And we said we could get that by adding pi. This is telling us that the cotangent of some angle is negative 5/4, which tells us also that the tangent of that same angle will have to be negative 4/5, right? So the tangent of the same angle is negative 4/5, and then what we would do then is look at the inverse tangent of negative 4/5. But when we do that, we get negative 0.6747, I think was what it came up with. And that would be an angle down here. Remember, this is all in radians here. All that's in radians, so we're at negative 0.6747 radians, that angle measure. We want the angle that corresponds to that, or that ends up in the second quadrant. We're looking for this angle here, actually. Okay. To get that, we say we could add pi. The main reason we can add pi is because if we come all the way over to here, to pi, we see that this part right here, this little piece, has to be the same numerical measure, the absolute value of that other angle measure across from it. So if we take pi minus that value, which is the same as adding pi to the value we initially got, we should get the angle measure. When we do that, when we add pi to this, we get approximately 2.47 for that one. Okay. That only happens, that part about adding pi to get over into the second quadrant, only happens when we have an inverse cotangent of a negative value. Okay? That's the only time. Any questions there on either of those calculator problems? You will be able to use a calculator on this test. Okay? But it has to be a real calculator. No cell phone calculators, okay? I'm telling you, I'll tell you that today. I'll probably tell you every class until we have the test, because I want to make sure everybody's heard it. No cell phone calculators for the test. Okay? Bring a real calculator. All right, number 4. Number 4, we have 2 cosine theta plus 3 equals 2. And we're trying to solve this equation. Now, the difference here is we're trying to solve this equation between 0 and 2 pi, meaning we want all possible solutions from 0 to 2 pi. Okay? So we're going to have 2 cosine theta equals, subtract 3, we get negative 1. The cosine of theta is going to be, then we're dividing by 2, so negative 1/2. And now we want the values of theta where the cosine is equal to negative 1/2. What values are those where the cosine is equal to negative 1/2? 2 pi over 3. And what was the other one? 4 pi thirds, right. Both of those have cosine values of negative 1/2, so therefore they are both solutions to the equation. And then the last one. The last one said 4 cosine squared x minus 3 is equal to 0. So we add 3, divide by 4, take the square root of both sides. On the numerical side, we do have to put plus or minus, so plus or minus the square root of 3/4. But that means the square root of 3 over the square root of 4, which is 2, right? So we want, and that should have been a theta in there. I said the other day, I don't think that part threw anybody about that being an x instead of a theta. I should have made it theta though. But we're still between 0 and 2 pi. And the values for the cosine have to be positive or negative square root of 3 over 2. So we're going to get 4 answers this time, one from each quadrant. Where the cosine is equal to these values, what kinds of angles have these values for cosine? Right, pi 6. What else? 11 pi 6. What else? 5 pi 6. 7 pi 6. Good. So all of those. Okay, all those are solutions. when the question just starts out, inverse tangent of something, whatever, like that, you have to think about the parameters, negative pi halves to positive pi halves, right? And those are the only answers you're going to give. When we're solving an equation from 0 to 2 pi, we want all possible solutions in all 4 quadrants, okay, if we're thinking of that unit circle. Does this help you see a little bit better what you might have had trouble with on this assignment? Just be sure to look back over it before the test next Thursday, because you'll see this stuff again, okay? It'll be there again. Anything else about that then? All right then. I think we're ready to go to the sum and difference formulas that we were starting to look at last time. They are in section 7.5 of your textbook. All right, so in section 7.5, sum and difference formulas. Last Thursday, just a brief recap here. Last Thursday, we looked at what those sum and difference formulas look like. And I think we worked with an example of something with the sine formula and something with the cosine formula, if I remember correctly. I don't think we did one with the tangent formula. Is that right? We didn't do anything with that. We just talked about, though, how if you have an angle that's not one of those we've already talked about, you know, that we're familiar with on the unit circle. If you have something, we specifically liked using things like pi 12s, 5 pi 12s, 15 degrees, things like that. Some angles are pretty easy to find exact values for through the use of these formulas. If it's an angle that you can add or subtract 2 of the angles that you already know about on the unit circle, then we can put them into this formula and crank out an exact answer. Okay, so that's what we were working on here. It also helps reinforce those unit circle values that we've been working with, hopefully, because we got to use those as well. I'd like to start off, I think, by looking at an example using one of the tangent formulas, okay? So let's do the tangent of 15 degrees here. I think that was actually a problem somewhere. I'm not on the right page, but I remember that one somewhere. That was number 17. The tangent of 15 degrees. So what angles can we add or subtract to get 15 degrees? (45 degrees minus 30 degrees. That works, doesn't it? 45 degrees minus 30 degrees. All right, so here's our alpha minus beta. That's what we're looking at, the tangent of alpha minus beta. What that formula said was this: tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. So we're going to plug into this formula here. We're going to plug in these values because we're working with the tangent of 45 degrees minus 30 degrees. See what we're doing? We're setting it up so that the angle we're trying to work with here is going to be a sum or a difference, right? A sum or difference of 2 angles we already know a lot about from the unit circle. So we're going to have tangent 45 degrees minus tangent 30 degrees over 1 plus tangent 45 degrees, tangent 30 degrees. Yes?
Do you have a calculator in degrees?
You don't need a calculator for this, ironically. Yeah, you don't need a calculator for this. If you were actually getting a decimal approximation, you would want it in degrees because it said tangent 15 degrees and get that. But we're trying to get that exact answer here, and we don't need a calculator for these problems. All right, so what we have here then is tangent 45 degrees. That one's not bad. What's the tangent of 45 degrees?
So 1.
Just 1, because square root of 2 over 2, square root of 2 over 2, right? I mean, it's one over the other. So square root of 2 over 2 over square root of 2 over 2. Okay? So we've got 1 minus something. Down here we've got 1 plus, and then the tangent 45 again is 1. And so far what I have not filled in is this tangent 30 degrees there. So we got to figure out what the tangent of 30 degrees is. Okay, so what's that tangent of 30 degrees going to be? Well, your 30-degree angle, what's the coordinates on a 30-degree angle? Square root of 3 over 2, 1/2 is correct. So the tangent of 30 degrees is going to be 1/2 over the square root of 3 over 2, right? That doesn't look nice. So it's 1 over the square root of 3. And if you rationalize that, what do you get? Square root of 3 over 3. Good. So that's what we're putting in here, square root of 3 over 3. So over there we figured out the tangent of 30 degrees over to the side. If we didn't have it in our heads there, that one might be a little harder to keep straight. I don't know. So what do we have now? 1 minus the square root of 3 over 3 over 1 plus the square root of 3 over 3. I don't like the looks of that answer. I don't want you to leave it like that. It's too many fractions together. We call it a complex fraction. It just looks bad, right? It doesn't make a lot of good sense. But we can get rid of some of those fractions in there. How are we going to get rid of those extra fractions?
You would multiply.
Multiply by what?
I'd say square root of 3 over 3.
Multiplying by the square root of 3 over 3 won't get rid of my fractions. Right now I'm just getting rid of fractions. If you multiply by the same denominator, 1 plus square root of 3 over 3, 1 plus square root of 3 over 3, you're not going to get rid of fractions, and you're not going to get rid of radicals. I think you're trying to rationalize, but you're not going to get rid of radicals. Right now I just want to get rid of the fractions. Help me out with that. Are we following? How can I get rid of the fractions? I get rid of fractions if I get rid of the denominators, right? How can I get rid of my extra denominators there? I am going to multiply by something. What can I multiply that by and clear out that fraction? 3. Good. The least common denominator is what you always multiply by. Okay, so multiply by that least common denominator. What does that give me over here then when I multiply? 3 minus the square root of 3. 3 plus the square root of 3. See where that's coming from? Y'all seeing that, where it's coming from? Yeah? Because what happened to those other 3's?
3 is the same as 3 over 1, so they just cancel out.
Yeah, they canceled. On the square root of 3 over 3 parts, the 3's are canceling, the denominator and numerator ones. Now, this answer I've got here, it is true. That is an answer. That looks a whole lot better. 3 minus square root of 3 over 3 plus square root of 3. The book might even leave it that way, but they might not because it is not rationalized. So they may rationalize that out. And if they're going to rationalize now, let's talk about what are we going to rationalize with here? What are we going to multiply by? The first thought was to use the same thing in the denominator, because if the denominator only said square root of 3, that's what we would do. That's actually not going to clear it out here. We have to multiply by what's called the conjugate of that denominator in order to rationalize. Do you remember conjugate? That word? What's opposite? Okay. And the opposite's not exactly the same as the conjugate, but you want the opposite sign in the middle. Okay? If we talk about an opposite of 3 plus square root of 3, that would be negative 3 minus square root of 3. So that's why I'm saying it's not exactly the same. All signs have to be opposite to be an opposite. But for the conjugate, we only need to change that sign in the middle. So we're going to multiply by 3 minus the square root of 3. The denominator determined my conjugate because the denominator is where I'm trying to rationalize. So since the denominator was 3 plus square root of 3, I want to multiply by 3 minus square root of 3. What I do to the denominator, I must also do to the numerator. All right, so now what am I getting up on top? Boil that out for me on top. 3 times 3, 9. 3 times minus square root of 3, I'll just write it all out. Minus 3 square roots of 3. Minus square root of 3 times 3, minus 3 square roots of 3. Minus square root of 3 times minus square root of 3 is plus 3. That's what I've got on top, isn't it, when I multiply? See my first, outer, inner, last, or my distributive property going on there? Everybody see it? That's good. What do you get in the denominator? Okay, so 3 squared, which is 9, minus square root of 3 squared, which is 3, right? Because we multiply conjugates. What happened to that stuff in the middle? Well, they added up to 0, didn't they, down there? Yeah, we had this and this, but they're opposites. So they add to 0 and go away. That's what gets rid of the radical. That's what makes us rationalize that part right there. So on top, it looks like I actually have 12 minus 6 square roots of 3 over 6. See where that came from? Everybody see my 12 minus 6 square roots of 3? Now the deal here is it's still not simplified. How do I know it's not simplified?
Because 6 goes into both 12 and 6.
6 divides into both 12 and 6. And it does have to divide into both of those for it to not be simplified. If that thing up there had just said 12 minus square root of 3 over 6, then we'd say we're done. It's good. But if there's a common factor with all three of these, I'll draw a little triangle between them. If there's a common factor between all three of those, then we're not done yet. So we get 6 divides into 12 2 times, 6 into 6 once, 6 into itself once. We don't need to leave it over 1. Looks like it's 2 minus the square root of 3. That's what it looks like. What's really happening there? We're factoring out a 6 up there on the top. That's what we really did. That's what we really did. But I just talked about it since he said 6 divides into all those. I just divided 6 into all three of them. That works out the same way. Maybe you like that better. You didn't have to think about factoring. I don't know. This is a long problem. Sometimes the book, I've noticed, sometimes the book will leave the answer right there. Sometimes it will take it to there. Okay. Just don't leave me all those extra fractions in. Like, don't leave it 1 minus square root of 3 over 3 over 1 plus square root of 3 over 3. If you leave 3 minus square root of 3 over 3 plus square root of 3, that's okay. All right? It's not rationalized, but that's okay. All right? Or coming down here is great, too. This made it look a lot simpler, but we had to get there. It's algebra, right? Questions on this problem. This was showing the use of the tangent formula. The tangent formula is a little bit more involved, probably because it's a fraction. I guess maybe that's why. Anything else on this one? Where anything went, came from, any of that stuff? Go ahead. Yeah, we're going to see another one with the tangent formula here in a minute. Anything else on this particular one?
The 45 degrees minus the 30 degrees. That's just we picked something that would fit in there and did it that way.
Right, because the original problem said tangent of 15 degrees. So we're just rewriting 15 degrees.
With two angles that we know.
With angles we know about. That's right. It has to be angles we know something about. Okay, that's why we don't need the calculator, because we already know something about these angles. Okay. Anything else on this one? It's very long. All right, let's try another one there. We'll go up to 14 because it uses radians, okay? That's no big deal, but Tangent of 7 pi 12ths. We looked at one of the problems last time using radians. And remember we talked about how the angles we already know about on the unit circle, we want to convert them into 12ths if we're going to use this type of thing to see which ones can add or subtract together to get this. Or maybe you want to just think about two numbers you can add and get 7 and see then how they would reduce. That might work too. See what I'm saying? I might be thinking, well, I know 4 pi 12ths and 3 pi 12ths will give me 7, right? Are those angles I know something about? They are. So I could use something that I just think of, oh, this adds to 7. I don't want to use 5 pi 12ths because I don't know anything about that. So I wouldn't pick that one. You may just want to start looking at your pi thirds, pi fours, pi 6 and see what they are in terms of 12ths. There's two ways kind of you can think about this. Well, I see here, though, that if I have pi thirds plus pi fours, I get 7 pi 12ths. True? Is everybody convinced of that much, at least, so far? We're convinced. Good. All right. Formula says, let me put the formula over here. This would be tangent of alpha plus beta. Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Here's my alpha. There's my beta. We're just plugging into that formula. Tangent pi thirds plus tangent pi fourths over 1 minus tangent pi thirds tangent pi fourths. All right, so tangent pi thirds. Tangent pi thirds. Your pi thirds angle, what's the coordinates?
Pi thirds would be or 1/2 and square root of 3 over 2.
Correct, 1/2 square root of 3 over 2. So the tangent at pi thirds is going to be what? Square root of 3, right, because it's square root of 3 over 2 over 1/2. So we got square root of 3 there, plus tangent of pi fourths, we already know that one. That was the one we like to use the best. So 1, and then 1 minus square root of 3 times 1. So that looks like square root of 3 plus 1 over 1 minus square root of 3. What if we rationalize that one? What are we going to multiply by?
Be the conjugate of 1 minus square root of 3.
Yeah, so 1 plus square root of 3, right? 1 plus square root of 3 down there. And what does that give us? Remember, you're multiplying the whole thing, so that's why I'm going ahead and grouping those first ones in parentheses to make sure we're seeing, it is a binomial times a binomial. All right, so on top I've got, it looks like square root of 3 plus 1 plus the square root of 3. In the denominator, I'm going to have 1 minus 3. So I've got 4 plus 2 square roots of 3 over negative 2. And so that would be what? Negative 2 minus square root of 3, right? Negative 2 minus square root of 3. Because the 2 divides in, the negative 2 divides into the 4, negative 2 times, into the 2, negative 1 times. So where I have that minus square root of 3, that's like minus 1 square root of 3. Okay. That's the tangent one. You all were working on some of these others here, 11 through that first part somewhere, even with the sine and the cosine. Did you get a chance to try those? Does anybody have a question about a sine or cosine one there? Yeah, go ahead.
35.
Okay. Are you on page 481? No? Okay. That's on the identities. Okay, hold on just one second. Anything else on these 481? We were just looking at a few of them there so far. So we'll come back and finish up this section here in just a minute. Let's go back then to, your question was 45? 35? Okay. Short memory here. All right. So looking back a little bit at this establishing of the identities. Okay. On 35, we were on page 470. We're trying to establish this identity. Secant 4 theta minus secant squared theta equals tangent 4 theta plus tangent squared theta. Okay. It doesn't really matter which side I pick to work with because they both look the same. You know, we said we want to pick the side that looks the toughest. These both look equal in difficulty. So which one will we pick? Which one did you pick or want to pick? Left side, just because we like to work on the left side. It's psychological. We like to work on the left side. All right, so the left side has to turn into tangents. We see all this tangent stuff on the right side. Remember, this side is our goal. That's where we're trying to get to. We want the secants to turn into tangents. And we do know, I mean, I'm seeing these secant squared theta, secant 4 theta. I don't know, maybe I want to do something with that Pythagorean identity. You know, the tangent squared theta plus 1 equals secant squared theta, that one. That's the one I would want to have in mind here. How do you think we want to do? What do you want to do with it? Just plug that in for secant squared theta. Do we want to factor out a secant squared theta? Those are pretty much my options. It looks like I can factor out a secant squared theta from the left side. I can just plug in for secant squared theta. Any suggestions?
Well, secant squared theta is equal to tangent squared theta plus 1.
Right, so what do you want me to do with that?
If you multiply that by 2, you also get secant 4 theta, don't you?
If you multiply by 2, you got to square it. Right? If you square secant squared, then you get secant 4th. Well, the more I'm looking at this one, the more I think we want to factor out a secant squared maybe. I don't know. What were you going to say? Let's factor out a secant squared. I think that's going to be maybe the way to go because here's what that does for us. It leaves us with a secant squared minus 1, right, for that left side. So, well, let me go under it. I think it helps if we just go under. The reason I thought I might want to do that is because now everything's in terms of secant squared theta, and I don't have that secant 4th theta anymore. And like y'all were just telling me, you know, the identity says tangent squared theta plus 1 equals secant squared theta. So it puts it more in those terms. So I know secant squared theta here is tangent squared theta plus 1. And I'm substituting that in place of the secant squared theta because I want to get tangent squared theta stuff on the right side. I want everything to be in terms of tangents over there. Isn't secant squared theta minus 1 tangent squared theta? That's the question. You agree? Tangent squared theta plus 1 is equal to secant squared theta, so secant squared theta minus 1 must be equal to tangent squared theta. Good observation there. That is equal to that. Okay. Well, now what? Just multiply it. We get tangent 4 theta plus tangent squared theta, which is the goal, right? That's what we were trying to get to. When we were establishing the identities, remember, we're just trying to show that one side of the equation does look like the other. It turns into the other. It is equivalent. So maybe that one wasn't too bad after we looked at it a little bit there. Is there another one from that part? The establishing.
Can you do number 39?
Yes, let's go to 39 here. 3 sine squared theta plus 4 cosine squared theta equals 3 plus cosine squared theta. Okay. Which side do we want to work with?
The left side, since it's more complicated.
Probably the left side, yeah. It looks a little more complicated because it's got a sine squared theta and a cosine squared theta, so that makes sense to me. And our goal then, keep your goal in mind, we're trying to reach this part over here. That only has cosine in it. It does not have a sine, so that might give me a clue what I might want to do first on the left side. What might I want to do first? Get rid of, which one? On the right side, I've still got a cosine. I don't want to get rid of my cosines. I want to get rid of my sines, right? Get rid of sine. Okay, so let's substitute something in for this sine right here. We'll have 3 times, what's sine squared theta? Other way. 1 minus cosine squared theta, right? Is there a difference in cosine squared theta minus 1 and 1 minus cosine squared theta? There's a difference, okay? So be careful. But we know that sine squared theta plus cosine squared theta equals 1. So therefore 1 minus cosine squared theta would be equal to sine squared theta plus the 4 cosine squared theta. I'll multiply this out, it looks like. 3 minus 3 cosine squared theta plus 4 cosine squared theta. What's that going to equal?
3 minus cosine squared theta.
How about 3 plus cosine squared theta?
Yeah.
Why is it plus? You see it?
Yeah, I see it.
Yeah. Okay, because we had the plus 4 and the minus 3. So 3 plus cosine squared theta is what we wanted, right? There we are. It brought us there. See how these things work? Got to manipulate them a little bit, do some substitutions. Now we have some of these with the sum and difference formulas also. So while we're thinking about establishing identities, let's pull one of those out here. I didn't show them to you yet. That was on my list of things to do today. Okay. Let me find it here. So still thinking about establishing an identity. This one is an example from your book on, it's number 48, over on page 482. Okay. It says the cosine of pi halves plus theta equals negative sine theta. And we want to establish the identity like we were just looking at on those last 2 problems. We want to turn one side of the equation into the other. Which side will you start with?
Left side.
Left. The left side I've got cosine of something plus something. Okay, that relates to this section we're in. This is like the cosine of alpha plus beta. So we need to use that formula and expand out what this cosine of pi halves plus theta would look like. Remember the formula. Cosine alpha plus beta equals cosine alpha, cosine beta, minus sine alpha, sine beta. Okay, that's the formula we want to use here. All these formulas are in your book on page 481, remember. Okay. All right, so this was my alpha, that's my beta. That's what it's acting like, right? So I'm going to say on the left side here, the cosine of pi halves plus theta equals the cosine of pi halves, cosine theta, minus sine pi halves, sine theta. Okay. Here's my goal. I'm trying to turn it into negative sine theta. I don't do anything with that other side though while I'm establishing. When I'm establishing an identity, I don't do anything with one of the sides. I just work with only the side I start working with, right? Nothing on the other side. All right, so the cosine of pi halves, what's up? 0. And cosine theta, and those are being multiplied if you're wondering. That's what's going on there, okay? Minus, what's the sine of pi halves? 1. Sine theta, okay? 0 times cosine theta, 0. This will be minus sine theta. So I just get minus sine theta. We just established an identity using an addition formula, a sum formula here. Questions there? Trying to turn one side into the other. Yeah, 0 times anything right there, so that turned into 0. And that part we worked together with, okay? What else here on this part? Let's look at one more with the sum and difference formulas establishing. Let's go to 58 down there. 58 looks like this. And this is still on 482. Cosine alpha plus beta plus cosine alpha minus beta equals 2 cosine alpha cosine beta. Again, we're going to use the formulas we know and expand this out. Cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. I'm just putting the formula up here for your use. And cosine alpha, I'm going to do something here different. I'm going to write two formulas in one. Is that all right? Now I'm putting under my plus sign, I'm putting the minus, because if I look down there, I'm going to look at cosine of alpha minus beta. If I'm looking at that, then over here in the worked out part, it's going to be a plus. That's the only difference. Okay? So if I've got cosine alpha plus beta, I'm going to have that top sign going, that minus. If I've got cosine alpha minus beta, then I'm going to have that plus sign going. Does that make sense what I'm telling you on that part? That's just the formulas up there at the top. 2-for-1 formulas. All right, so this first part here, cosine alpha plus beta, I've actually got to write out the formula. Cosine alpha, cosine beta, minus sine alpha, sine beta. Now I'm to that plus sign. Now I've got to work on this cosine alpha minus beta. That'll be cosine alpha, cosine beta, plus sine alpha, sine beta. What does that stuff equal? There's things I can put together there, right? Some like terms. I see cosine alpha, cosine beta, plus cosine alpha, cosine beta. So that'd be 2 cosine alpha, cosine beta. Yeah, that's minus sine alpha sine beta plus sine alpha sine beta. So that's nothing there. They add to 0. That's what we wanted right there. Okay? That's where we were trying to get to. It's just helping you think about these formulas, expanding them out, seeing how they work. That's what we're doing there in that part. So the formula could already be expanded out, and you might have to condense it and see what the thing's equal to. Still working with these same formulas here. Does anybody have anything else on 58 you want to talk about on 58? Okay, because I've got a formula or an expression I'm going to put up here, and let's see if we can take it back into the formula. It looks like this. And you do not need a calculator. Sine 20 degrees, cosine 80 degrees, minus cosine 20 degrees, sine 80 degrees. Okay. We want to find the exact value. You don't know anything about a 20-degree angle, an 80-degree angle. You don't know what these values are, right? You don't know these. But hopefully you recognize that this looks a little bit like this. It looks a little like sine alpha, cosine beta, minus cosine alpha, sine beta. Isn't that what it looks like? That's where it's come from. What formula was that for?
It's sine of alpha minus beta.
Sine of alpha minus beta. That's the formula for that. So this thing we're working with here must be the sine of something minus something. What's my alpha and my beta?
20 degrees and 80 degrees.
So 20 degrees minus 80 degrees. The way it's written out, right? That would be the sine of
Negative 60 degrees.
negative 60 degrees. And the sine of negative 60 degrees is, we do know that, is it negative 1/2? That's what I'm hearing.
So positive
Negative.
1/2 negative square root of 3 over
Negative square root of 3 over 2, right? Negative square root of 3 over 2. If we're at negative 60 degrees, remember where that is. The point on the unit circle would be 1/2 negative square root of 3 over 2. Okay. So now we know that sine 20 degrees, cosine 80 degrees, minus cosine 20 degrees, sine 80 degrees is actually just the sine of negative 60 degrees, or negative square root of 3 over 2. That's what we get there. The formula was already written out for us here. We had to take it back and condense it. Does that make sense? Instead of, before, what we were doing was expanding out the formula. We were having things like, the sine of, we didn't have a negative one, but the sine of an angle, and we wrote it out, sine of something plus something, something minus something, and expanded that expression. Now we have condensed it back into what we would have started with. Let's try another one like that one. I think we'll do a tangent one here. This one is 28 off of page 481. Doesn't much look like it says 28. We have the tangent of 40 degrees minus the tangent of 10 degrees over 1 plus tangent 40 degrees, tangent 10 degrees. Okay. So what does this look like? Tangent alpha minus tangent beta over 1 plus tangent alpha, tangent beta, right? Which happens to be the formula for?
tangent alpha minus beta.
Yeah, tangent of alpha minus beta. So over here you are telling me then it's going to be the tangent of 40 degrees minus 10 degrees. So that's going to be the tangent of 30 degrees. Which we worked with that 30 degrees a while ago, didn't we? Coordinates at 30 degrees, square root of 3 over 2, 1/2, square root of 3 over 3, right? Y'all got that one memorized today. All right, square root of 3 over 3, tangent of 30 degrees. Everybody see where that came from? Tangent 30 is 1/2 over square root of 3 over 2. We get 1 over square root of 3. We rationalize, we get square root of 3 over 3. Okay, that's where we're getting that from. So these aren't too bad. You just have to recognize what to do with them, that they're already out in the formula and you've got to condense them back in. One other thing we're going to do with these formulas today. Okay, it's still in section 7.5 here today. It's a big section though. What if we just have some general knowledge here and we want to know what the sign of the alpha plus beta, alpha minus beta, cosine of some of these, or tangent is? We can work with those as well, even if we don't know what the angles are that's involved. So let me grab one here so you can see what it looks like. This is 34, still on page 481. Cosine of alpha, square root of 5 over 5. 0 is less than alpha. Whoops. Less than pi halves. And then over here it tells us the sine of beta is negative 4/5. And negative pi halves is less than beta is less than 0. Okay? That's what we're getting there. Question. Okay, the question here is, we have actually, they've got 4 parts here. Part A is going to be the sine of alpha plus beta. Part B, cosine alpha plus beta. You get the idea here of what they're asking. Part C, sine of alpha minus beta. And part D, tangent of alpha minus beta. We're going to do part A right now. Let me put find sine alpha plus beta. We want exact values again. All this stuff here is exact values. You might want a calculator on some of this to help you multiply, but you don't need a calculator to get the actual answer. You know what I mean? We're not punching in sine of something here. All right. What do we know? We know the sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. We do know that. Just trying to separate that from the problem, what we were given there. In the problem, they gave us 2 of these parts. They gave us the cosine of alpha right there. They gave us the sine of beta. We know 2 things that go into this formula. We do not know what alpha and beta are equal to. We do not know those angles, but we're not going to have to know them. Okay? As long as we know the sine and cosine of alpha and beta, we can work in the formula. Let's draw. A lot of you like to draw your angles out, right? Let's draw alpha. Where's alpha going to be? If the cosine of alpha is square root of 5 over 5, and alpha, it tells us here, alpha is between 0 and pi halves, where's alpha? It's in the first quadrant. Okay? Alpha's there in the first quadrant. All right. So, if alpha's there in the first quadrant and the cosine of alpha is square root of 5 over 5, what's that telling me about?
The x value is the square root of 5, and the r value is 5.
So it tells me that much, right? I need to know the sine of alpha. I've got to know the sine of alpha for my formula here. So I'm going to have to know what that y value is. So I've got x squared plus y squared equals r squared. Okay. 5 plus y squared is 25. That tells me y squared is 20. And y is going to be the square root of 20, but that simplifies to be what? 2 radical 5. 2 square roots of 5, right? $20 was 4 times 5. Square root of 4 is 2. Square root of 5, we can't do anything about that. So y is 2 square roots of 5, which what I needed to know that for was to get the sine of alpha. What's the sine of alpha? 2 square roots of 5 over 5, right? So that's what I'm going to use right there for the sine of alpha. See that? I'm going to be using this here for cosine of beta. Use that there. I still need to find the cosine of beta. That's what I need now. Let's work on beta over here. All right, so when I work on beta, which quadrant's beta located in? Beta's in which quadrant? It's telling me right here. Let this stuff help.
That'd be the fourth quadrant.
It's in the fourth quadrant, right? If beta's between negative pi halves and 0, it has to be in the fourth quadrant, doesn't it? Between negative pi halves and 0. So beta's down here somewhere that we're looking at. And we know the sign of beta is negative 4/5, so we know y equals negative 4, r equals 5. We're going to need to know x because we want to know what the cosine of beta is for our formula. What's x going to be? Y'all might not even have to work this one out. Y is negative 4, r is 5. It's one of those common Pythagorean triples. It's a 3, right? 3, 4, 5, right? Even though one of them's negative there, it didn't matter. But 3, 4, 5. So x is 3. The cosine of beta then is what? 3/5. Okay. Now we've got everything we need to fill in the formula and figure out remember what the question was after all that work? Do you remember the question? Sometimes it's hard to after that long. The question was find the sine of alpha plus beta. Okay, so if we're finding the sine of alpha plus beta, let's come down here a minute. Sine of alpha plus beta. Following that formula from up there, I've got the sine of alpha, which was 2 square roots of 5 over 5, times the cosine of beta, we just found it was 3/5, plus the cosine of alpha was in the original problem, square root of 5 over 5, and times the sine of beta, again in the problem, negative 4/5. We're just multiplying here, multiplying and adding. What do you get for that first part?
6 times square root of 5 over 25.
Right, 6 square root of 5 over 25 plus, oh, is it plus? No, it's not going to be plus now because we're multiplying times that negative 4, so minus 4 square roots of 5 over 25. What does that equal? Got to remember stuff about radicals, don't we? What's my answer?
Be 2 square root of 5 over 25.
Right, 2 square roots of 5 over 25. Well, that was the sine of alpha plus beta. That was part A only. That was part A. Okay. Now, the good news is, though, like, part B, it's going to ask you for the cosine of alpha plus beta. Part C, the sine of alpha minus beta. You've got all the information already there that you need for those things. You're just plugging in to different formulas. That last one, you're going to need a little bit more, that tangent of alpha minus beta. Let's go ahead and run through the tangent there. Any questions so far on getting through the sine of alpha plus beta? Are we seeing it? We're plugging into that formula based off our drawings from our given information. Let's do that tangent part. We'll have to maybe flip back there and remember some of that. 34D says find the tangent of alpha minus beta. We know from the formulas the tangent of alpha minus beta is tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. All right, so what did we know about this alpha and beta stuff? We didn't do anything with the tangents yet, right? But back on our other screen, okay, from previous page or on your notes, you might be able to see without going to the previous page. We should be able to find that tangent of alpha and tangent of beta pretty easily. Let's go back there and see. All right, here's my drawing about alpha. It's on the red graph here, my drawing about alpha, right? So what's the tangent of alpha going to be? Y over x. I've already got my drawing. I've got my information. So what is it? 2 square roots of 5 over the square root of 5. Which is actually just what?
2.
Just 2, right? So let's look back, because the square root of 5's cancel. Let's look back at the tangent of beta. Beta's over here on the black graph. Tangent of beta looks like it's -4/3. See that? Where I'm getting those? -4/3. Let's plug those into this formula. That's all we needed to get from there. We've already drawn the picture. We've already done the work. We found the x, y, and r. We can find all these values now. So tangent alpha, 2, minus tangent beta, -4/3, over 1 plus 2 times -4/3. So on top, that's really 2 plus 4/3. Down here, what do I get down in the denominator? If I just simplify that out.
Be 1 minus 8/3.
1 minus 8/3. Yeah, let me caution you about something on that denominator. We're not adding the 1 plus 2. Okay, somebody asked about that in another class. We're not adding 1 plus 2. It's 1 plus 2 times -4/3. And multiplication comes before addition, right, in our order of operations. So maybe we can put that 2 in parentheses also if that helps see it. But it's multiplying by the -4/3. All right, so here we've got something like we had in that tangent formula before, and we didn't like all those fractions. We could get rid of the fractions now. There's nothing against that. I mean, you can go ahead and simplify by combining 2 plus 4/3 if you want, or you can clear out those fractions like we did before if you prefer. What are you going to do? Multiply everything by 3, or go ahead and get common denominators and combine? What's your preference? Multiply by 3? Yeah, I think it'll work out just as well to do that like we did before. If you multiply here by 3 and here by 3, you get, what, 6 plus 4 over 3 minus 8. 10 over -5, which is -2. And you didn't have to, turn 2 into something with the denominator with 3 and all that. Not that those are a big deal to do, but I know a lot of people don't like fractions. Or at least that's what I hear. At least that's what I'm told many times. So it came to my attention on the My Math Lab quizzes, there's a problem on quiz 7 that I need to move to a different place because it does not fit with that material on quiz 7. I don't know how it got in there. It's not covered at that point. So I will be moving that. So if you get to that problem on quiz 7, and it's problem number 7 on quiz 7, we have not covered that yet, okay? Don't worry about that problem. Somehow I'm going to take it off of that quiz, okay? Don't let it bother you there. So you've still got some My Math Lab quizzes to be working on. If you've not done any of those for Chapter 7, be working on those. I'm going to be giving you some study problems from the textbook to help start preparing for the test. I don't have those today because today I'm just giving you study problems from section 7.5, what we've been working on. I think that's enough for you to be working on between now and Thursday. But on Thursday, I'll give you some more practice problems from the review part of the textbook, okay? And then we'll have our test then next Thursday. Let me give you some practice problems right here from this section, 7.5. It's over on page 481 and 482. You all were already working with 11 to 17, right? So let's add to that a little bit. Let's add to that 23 through 37 odd. And 47 to 53 odd. That last part's just a few more of those established identity where you have to use the sum or difference formulas like we're using in this section. And you can start working on your My Math Lab quizzes for Chapter 7. Actually, I hope you've already started on them, but maybe not. And we're having a test next Thursday. Okay. Anybody have a question? And let's see, what else was I going to tell you there? Anything else? Anybody had a question here? What's next Thursday? Day before Halloween, I guess, right? Oh, what's next Thursday? The test. Is that what you said? Yeah, that's right. I meant the date, but that's okay. I like that. Yeah, next Thursday's the test, whatever the date is, right? All right. You all have a great day, and I'll see you back then on Thursday, okay? And Cheyenne, I didn't get your email replied to yet, but I'm going to reply to you here in just a minute, okay? So just
Okay,
so
that's fine. Thank you.
Okay. I did see that, though.
What are you hacking into over there?
Oops, I didn't realize my mic wasn't on. Sorry about that. I was answering you.
Oh, that's okay. I thought that was someone else beside you.
Oh, yeah, it
you
is.
co-
That's one of my students, yeah.
When are you coming over?
Tuesday. Next Tuesday, though. Okay.
Oh
Rob
yeah,
had
that's fine. Yeah.
Rob had asked me to wait because of him being out of town. And so, or that's what I understood anyway. Maybe we just all got our wires crossed over here. I don't know. So I know. But thank you all for getting everything together over there.
Oh, no problem. No problem.
So is there a symposium for me to write on over there? I mean, everything's pretty much.
There will be.
There will be? Okay.
There will be.
Okay, great. Sounds wonderful. All right, well, thank you then. See you next week there. Well, I'll probably see you Thursday too.